we're going to design the circuit in figure 1.b. We previously did 1.a, which is unity gain buffer, and that is in the playlist link below the like button, and it's going to be a very good starter for this. But now we're going to do 1.b. So my lab partner has constructed the spice simulation and done the hand calculations for the given values. But what we're going to do is use a multimeter and measure our resistance to get the actual values, not the measured ones. And then we're going to construct the circuit, and we're going to do that on the breadboard. We are then going to add a 10 kilo ohm load resistor to our Vout node to see how this changes our voltage gain. And then we're going to add the same load resistor to our VP to see how that changes our voltage gain. So 10 kilo ohm resistor is going to be added to the Vout node, and then we are going to add the same load resistor to the VP node. All right, so let's get started. So looking at the breadboard, this is from the previous lab. Again, this is 1.a, and so what I'm going to do here is, since we use a lot of the same connections, all I'm going to do is disconnect these wires. Now, make sure your wave gen is off, your master enable is off, so there's no power running to this. And so with that, we can take out these 3 wires, just so that we have more room on our breadboard to work with. Now, we have this wire is going from Vout to our negative input. That's okay. Now, we want a wire to go from our positive to our any place on the breadboard, because we need to make a node. So we take this and we're going to place it, we'll just place it out here. And so this column right here is our node, because it's going to get power from our VP. And so let's do one thing at a time. Let's do our R2 first. Well, my lab partner has chosen our R2 to be 2 kilo ohms. And so we are going to use this resistor. I measured it with my multimeter already, and this is about 2 kilo ohms. It's exactly 1.969 kilo ohms, and that's going to factor into our percentage error later. So we're going to take this R2, and we want to put it into ground. We know that our negative rail is our ground, so we're going to just take this and plug it straight into the ground, just like that. So we can see that one of the leads goes into ground right here, into the negative row, and then the other lead is in the same column as this yellow wire. And so that's our node there. Now we want to go from our VP, which is the yellow wire, to an R1 to our voltage input. Now our R1 we chose to be about 1 kilo ohm, and that's exactly, I think, 0.993 kilo ohms. So we are going to put it in the same node as the yellow, so that's the same column that goes there, and then we can just put it into any space that we want up here. And I'm going to plug it in just right there. And so now we need our V input. That's our yellow wire. So we're going to take it and we're going to plug it straight into this resistor. We want to measure this, so we're going to take our orange wire and plug it into that same column as well. So it's going to go right there, same column. And then this blue wire, we want to measure our output, so it's going to go into the output. And that should be it for this circuit. Now we are going to go back to our waveform. We're going to click run all on our wavegen. We're going to click run here, and our master enable should be on. So looking at this, I did counter a little bit error, and I turned this off. I turned the master enable off because we do have an error here, and it's in our breadboard as well. So I read the measurements wrong, and actually our R2 is 1 kilo ohm and our R1 is the 2 kilo ohms. And so all we're going to need to do is switch a resistor, because this 2 kilo ohms is going to be in our R1 place, and our R1 is connected to our VP. So this resistor is going to swap out with this one. We're just exchanging it, so it's going to go in this column right there, and then this one is going to go to ground. So we're going to ground this one out. Now we can go into our waveform, we can master enable on, and then we are going to get these proper values. In dividing our voltage output by our voltage input, we're going to get approximately 0.3385 volts. This is very close to 1/3. The percent error here is 1.55%. So to calculate the percent error, we would take our actual value, 0.3385, subtract it from the measured value, which is 3, divided by the measured value, which is 3, and then multiply it by 100%. And so our percent error here is about 1.55%, which is in our plus minus 10% ballpark. And then if we use our resistors, and we use the voltage divider, which is the V source, and then we set it equal to, or I'm sorry, we have our V output and we set it equal to the V source times the resistor that it is over divided by both resistors, then we're going to get about 0.33525, and this gives us a percent error about 0.57%, because we take 0.33525, subtract by 3, divide that result by 3, multiply by 100, and that gives us our percent. And so that is it for our waveform. Now, looking at our lab report, we have the following. It says unity gain buffer. We have our diagrams here. We have hand calculations by my partner for the actual values. And then we have the SPICE simulation. And then we have a short description about this. Then we have our results on the breadboard in our waveform, and the talk about the output and what values we used here. Next, we are going to be looking at our non-inverting amplifier, but just a little added. If we add a 10 kilo ohm resistor to our V out, we can see what happens. So I'm going to pause this, and then we can run a waveform, and we can see that it looks approximately the same. So unless I'm doing something wrong, then they are approximately the same values, and adding the 10 kilo ohm resistor did not really do much. We have, if the resistors used to construct the circuit have a tolerance of plus minus 5%, how much variation will there be in a normal attenuation factor of 1/3 when a million of these are manufactured? And attenuation means the reduction of the amplitude of a signal, electric current, or other oscillation. Well, if we have a tolerance of plus minus 5%, we can think of the worst possible thing, which would be the plus or minus of 5%. So if 1/3, if we have our attenuation factor of 1/3 for millions of these, then the worst possible thing that could be is that we have 1/3, and then with our tolerance of plus minus, we could just say plus 5%, and that would be the worst thing. So there would be quite a lot of variation here, relatively. And that's it for this one. Again, next video we're going to be looking at the non-inverting amplifier, which is a little bit bigger of a circuit.